the recording.
Okay, thank you. Thank you. So let me start the Cracovia session. I'm Mikołaj Leszczuk from the AGH University of Kraków, Poland. Just to remind you, the Cracovia stands for Quality Assessment for Computer Vision Applications. There are three chairs, co-chairs in Cracovia, but it seems like I'm the only one attending this meeting. The other ones are Patrick Lecalette from the University of Nantes and Lu Zhang from INSA Rennes. And today we have three presentations. The first one is probably going to be the shortest one, and it's so that's why it was scheduled as the first one. It's going to be presented by me myself together with Jingwen Zhu, who is already attending. The title is The Ground Truth Coordinates for Automatic License Plate Recognition. The second presentation is I need to check the number. It's 223, and it's going to be presented by Hanene Brachemi. Unfortunately, I'm not sure what is the Hanene's affiliation, but I hope she will tell us. And the title is The Evaluating Vulnerability of Deep Learning-Based Image Quality Assessment Methods to Adversarial Attacks. And the third presentation is probably going to be the longest one. It's Alban Marie from INSA Rennes. And the topic is exploration of lossy image coding trade-off between rate, machine perception, and quality. So let me start with the first presentation. I will share my screen. It's probably going to be a rather short one. Okay, let me share it. Okay, can you see my slide? Just wanted to be double sure if you can see it.
Yes, yes.
Okay, perfect. So, as I mentioned, the title is The Ground Truth Coordinates for Automatic License Plate Recognition. Basically, it's going we're going to talk about the database, the annotated database that has been recently published. The work is authored by, besides me myself, is also Jingwen, who is with me right now. I mean, remotely, of course, but she's connecting, and also Yuding Wang. Currently, Jingwen is with the University of Nantes, and Yuding is with the INSA Rennes. However, at the time when the database was being created, they were both the interns at the AGH University in Kraków, Poland. So that's why we made it together. The presentation is going to be presented both by Jingwen and me myself. I will start, then she will tell you a little bit about the process of annotating, and I will make some final notes. Let me start with some introduction. Basically, we are talking about the ALPR. And ALPR stands for Automatic License Plate Recognition, and is the technology that allows us to identify and to read the vehicle license plate numbers. And this is being done using some digital image processing. So that's why it's in line with the Cracovia session. However, we are talking about the process of the ALPR, which may happen in the non-ideal weather conditions or acquisition conditions. So today we are going to focus about the database of annotated images, or actually video frames, with the ground truth coordinates in the ALPR, which can allow for the quality evaluation in the case of ALPR. It's quite important because you know, ALPR is used quite commonly nowadays in various applications like traffic surveillance, like law enforcement, like smart city projects. So having the ideal or, you know, well-performing ALPR, it's quite important if we want to have, you know, these applications running. The database is actually based on the video corpus that has been recorded at the AGH University of Kraków in Poland. And that was recorded as the footage coming from the CCTV cameras that were installed at the building just in front of the parking lot. And the database, the compiled database encompasses approximately 15,500 frames in total, which are obviously divided into several short video clips. And okay, before I will pass my voice to Jingwen, I would like to mention three things. First is what we call here as the ground truth annotation. So basically, the ground truth annotation is the process in which we, or in this case, that would basically Jingwen and Yuding themselves spend a lot of time manually labeling the image data with the correct information about, you know, where the license plate is located and what is stated on the license plate number. So this can ensure, you know, very high accuracy in training and also in evaluating models for the ALPR. Whenever we mention the coordinate formatting, we mean by this the specific way in which position and in which dimensions the license plates are represented in the dataset, and which is quite critical for the accurately, you know, locating and recognizing the license plates. And whenever we mention the data annotation naming convention, it's just the systematic methods that was used by the group or the researchers for naming the files. So whenever someone wants to download the database, it's quite obvious, you know, how to relate, you know, the actual video frames and the annotations. Right? So it actually facilitates the data management and the retrieval, and is quite essential for a large database as the one that we have here with the 15,000 images. So I think this is the last slide that I'm about to present. Then I will pass the voice to Jingwen. So we actually prepared like a ground truth database for each video in the data set. There is a corresponding text file that contains the ground truth information. It was prepared in such a way that it's quite easy to make the correlation between the videos and the frames and the ground truth data. And each of these files lists the coordinates that are specifying the location of the license plate of the individual names, and also it's possible to download the ground truth of the actual contents of the video of the license plates, meaning the characters and the digits that are displayed there. Okay, so now I will ask Jingwen to continue. So this is the demo.
Okay, so the first step of annotating the license plate is to develop a tools of annotations. So we developed an interface to annotating as shown in this demo. There is a cross cursor. We just click on the four corners of the license plate, and then the position of the coordinates, the point we clicked will appear at the top left of the interface, and it will return us the coordinate of the license plate. And next slide, please.
Okay.
So with this annotation software, we generate the ground truth file. The coordinates are formatted as follow. The first column is the name of the frame. So in the entire video, we can see a lot of lines corresponding to the frame 1, frame 2. And then there will be 8 number following the frame number, which includes the information of the position of the license plate. Next slide, please. So the X1, Y1 is the top left corner, X2, Y2 top right, etc. You can go to the next slide maybe. It's just in how to say clockwise order, which is consistent with our notating tools, the four corner of the plate. And then next slide, please. There are some special cases. For example, as shown in the left figures, the license plate is fully occluded. It is out of the image. So at this case, we just put all zeros to say that there is no license plate. And the second special case is the license plate is part of the license plate is occluded. So we just annotated the portion which are annotated, which are shown in the frame. That's it. I pass the floor to Nicola.
Okay, and so if anyone is interested in making any research on the top of this database, it's available under this link. I think later I will also copy this link to the chat, so you can click directly. The presentation has been already uploaded to the server according to Margaret, so you can also download and click the link from there. So it's pretty easy to download both the videos and the annotations. And on the right-hand side, you can actually see how it works in practice. So since you don't have always the fully rectangular license plates, then it's since you have the 4 corners, you can actually examine non-rectangular license plates like here in this figure. And of course, what could be the application areas? There are many of them. Actually, we also made some research on the top of it. I will just on the next slide, I will point you to the paper where our research is presented. But we see many application areas, like whenever you want to train and to evaluate the quality of the video footage for like traffic efficiency and safety applications, or for some law enforcement and security measures, and for any projects dealing with the smart city or the infrastructure development. I believe there is a room for the database like the one that we have created. And we also so just to make the recap, so it's 15,500 frames from the video footage. It was annotated, so you can download it for free. And we're also addressing the issue of partial and total occlusions, and everything is provided in a rather easy format. And yeah, it's quite easy to be used for many applications dealing with the computer vision. On the top of it, we also made a publication which is available here. It was published like I think 2 months ago or 1 month ago, quite recently this year at least. And there we both report the ground truth database and the research that was made on the top of it. However, the research that was made on the top of it was already presented on the last VQEG, so I didn't want to repeat my presentation. So you can actually come back to the previous VQEG when I presented the research. But that time, the database was not yet published, so that's why I was not presenting the database yet. But now it was the time we published the database as well, so that's why we have this extra presentation dealing with the database. Okay, that's basically everything. As I told you, this is going to be a quite short presentation. I don't know if you have any questions. Okay, I don't see any questions. So let me stop sharing right now. As I promised, later I will also copy paste the link to the database. And I believe now it's time for the remaining two presentations of this session. The first one is going to be presented by Hanene Brachemi. I hope I'm pronouncing your name more or less correctly. If not, please correct me. The title is Evaluating the Vulnerability of Deep Learning-Based Image Quality Assessment Methods for Adversarial Attacks. So, Hanene,
good afternoon.
The floor is yours.
Thank you.
I will switch off my camera to save bandwidth.
So I don't know if you can all see my screen.
Yes, we can see your screen. Perfect.
So good afternoon or good morning, depending on your time zone. My name is Hanan Brachmi. I'm affiliated to both INSA and EUTR Labs, and today I will be presenting our paper that we worked on along with my supervisors, namely Sid Ahmed Fizza, Wassim Hamidouche, and Olivier Desforges, and that is entitled Evaluating the Vulnerability of Deep Learning-Based Image Quality Assessment Methods to Adversarial Attacks. So thank you for being here today. As you might have guessed from the title, our work's main objective is to investigate the security aspect of deep learning-based image quality assessment metrics. So by the end of this presentation, you will hopefully have gained insight on how to launch an actual attack on a deep learning-based system in general, and against no reference deep learning-based metrics in particular. So here's also a little roadmap to help you to guide you throughout this presentation. I will first begin by providing a comprehensive overview of the study's context, and then briefly go through the related works or any necessary background that would help you have a better understanding of our proposed approach. And then I will be explaining the underlying intuition behind our actual proposed approach, followed by our experimental study and its obtained results. And finally, we'll wrap up with a conclusive summary of this research. So with the fast development of digital technologies, images are becoming omnipresent, whether it be on social media, in advertisements, and across various online platforms. But the thing is that these images are, however, constantly subject to impairments that could take place due to the different processes of the transmission pipeline, such as compression, enhancement, pre-processes, storages, and so on. So it is with no surprise that the concept of image quality assessment holds immense importance in this context. Now, on the other hand, according to a survey that had been conducted by McKinsey & Company in December 2022, the adoption of AI by different organizations has more than doubled since 2017. And while organizations are progressively integrating AI technologies into their operations, the cybersecurity risks that comes with this deployment is their primary source of concern. And well, their concerns seem to be well-founded, since in 2013, Szegedi had demonstrated that it was in fact possible to fool a deep classifier by carefully crafting some noise image that can be added to the input image in order to generate some adversarial image. So in what follows, we'll refer to the noise image as the perturbation image. And to summarize, the adversary's objective is to optimize this perturbation image and blend it with the clean image in order to generate this adversarial image. The adversarial image is ideally supposed to be very perceptually similar to the clean image in order for the attack to not be detected by the users. But the objective is also to make it yield a different output when inferred by the same model. So to cope now, if we go back to our image quality assessment context, whether it be by making the image quality assessment metric predict a good quality score for a poor quality image, or by trying to increase the latency by triggering different pre-processes or enhancement mechanism in the process in the transmission pipeline. For example, by making the image quality assessment metric predict a poor quality score, even if the image is of good quality. Anyways, in both cases, the adversary could significantly decrease the quality of experience of the end user of a certain platform, which could have serious economical consequences. But in a more serious case scenario, image quality assessment metrics are usually incorporated in end-to-end decision-making pipelines in order to make sure that the model's prediction is not biased because of the poor quality of the inputs. So if we were to make the metric predict a good quality score for a poor quality image in a medical context, for example, that would most likely lead to an incorrect or biased diagnosis. So I think that at this point, now it becomes evident that considering the robustness of an image quality assessment method is just as crucial as evaluating its performance. Let's now explore the existing attacks in the literature and how it becomes possible to extend them to the image quality assessment context. More globally or more generally, attacks can be categorized in the literature either according to the adversary's objectives or according to the adversary's knowledge on the model or the metric they're trying to attack. According to their objectives, into targeted, where the goal is to make the model predict a predefined label or predefined score by the adversary, or untargeted, where the actual objective is to vaguely jeopardize the good functioning of the model. They can also be classified into white box, black box, and gray box. White box being the case scenario where the adversary has a full knowledge of the model's architecture, its weight, data it had been trained on, and so on. And black box being the other extreme opposite, where the adversary has no actual knowledge about the metric they're trying to attack. Now, mathematically speaking, any attack can be formulated using a simple optimization problem. A targeted attack, for example, can be achieved by minimizing some empirical risk, or rather some loss function that is computed with respect to the perturbation image or to the adversarial image between the target we're trying to achieve and the actual prediction we're getting on the adversarial image, under the constraints of X adversarial being still perceptually very similar to the clean version. On the other hand, the untargeted attack consists in maximizing the loss function between the correct score and the score we're getting on the adversarial image under the same constraint. Now, the same procedure is followed in the image quality assessment context, where the existing works propose to solve the optimization problem either using the gradient descent method or using a universal adversarial attack approach. The constraints, on the other hand, are verified by taking into account the edges information or the frequency information when trying to incorporate the perturbation image or blend it with the clean image. Now, another interesting approach that has been proposed consists in trying to integrate the constraints on the visibility within the optimization problem using KKT conditions. And in order to achieve that, they try to model the just noticeable difference using a full recurrence metric. And so the resultant optimization problem becomes then a Lagrangian combination between the optimization problem and a maximization of the similarity score between the original clean image and the adversarial resulting image. So to summarize, even though a few works have already been proposed in the literature to tackle the security aspect of no recurrence metrics, none of them actually investigates these attacks on actual deep learning-based metrics. Previous works do not investigate the relationship between the visibility of the perturbation and the efficiency of the attack in this particular case scenario. And most of the studies focus on the targeted setting, leaving the untargeted setting much less investigated. So having covered the existing works in the literature, let's now introduce our proposed approach. The main idea is that if we use a no-reference image quality metric to infer a clean image, then we're most likely to get a quality score that is correlated with the human estimation of the quality. So now the adversary's objective is to optimize some perturbation image that they will blend with the clean image to generate an adversarial image. And so this adversarial image is inferred using the same image quality assessment metric, but will most likely yield a quality score that is incorrect and different from the score that is predicted on the clean one. So in our study, we also mentioned earlier that we aim to further investigate the correlation between the visibility of the perturbation and the efficiency of the attack. So we start by relaxing the constraint on the visibility. Then in order to further adapt our attack to the in-targeted mode, we try to get an estimate of the ground truth, namely the mean objective score of the image given the predicted score by the model. Now, before delving further into the mathematical details of the estimation, we give the standard deviation formula of a set of points capital F that follows the Gaussian distribution. And one actual interesting property here is that if we sample the point S from the set capital S, then we have about 98% of confidence that this point will land among the interval that goes from the mean minus 3 times the STD and the mean plus 3 times the STD with increasing probabilities the closer we get to the mean. So here's the idea. Given the root mean squared error formula, we can notice that it is pretty much very similar to the given standard deviation formula. So ideally, first intuition was that we could consider the root mean squared error as an error margin, which would suggest that the mean objective score could be given by y predicted plus minus the root mean squared error. But in reality, this property is neither verified nor valid. So instead, we would rather consider a larger confidence interval and assume that the ground truth belongs to some interval that could be achieved by replacing the mean by y predicted and the standard deviation by the root mean squared error. Now, that being said, our estimation of the ground truth is given by sampling 10 values from this interval and computing their average. Moving on, let's now elaborate our obtained experimental results. So we conduct our experiments on two different image quality assessment datasets, namely Connect 10K and TID 2013. One contains sensitive distortions and the other contains authentic distortions. And we target three of the most commonly used TNNs in the literature, namely ResNet 50, VG16, and Inception V3. Using both targeted and in-targeted settings. We also illustrate the performance of the architectures in terms of Spearman ranked correlation score when being attacked using three classical, very simple but state-of-the-art attacks, namely FGM, BIM, and PGD, using different values of epsilon, with epsilon denoting the intensity of the attack. We also refer to the initial performance of the models on the clean test set using this red dotted line. And so overall, our empirical results show that our attacks do have an impact on the performance of the models regardless of the architecture, regardless of the dataset, and regardless of the values of epsilon, since we can notice an evident decrease in the disbursement correlation score on the attacked images or adversarial images. And in order to further investigate whether the visibility of the perturbation has an actual impact on the effectiveness of the attack, we plot our attack's success score with respect to the ALPI-IPS score that is computed on the test set. For the record, we define the success score of our attack as the gap that exists between the initial performance of the model that is computed on the clean test set and the correlation score that is computed on the altered or the adversarial test set. So normally it is supposed to vary between 0 and 2 with a higher value referring to a higher performance of the attack. And so I think that given the empirical results, it is safe to say that both attributes seem to be pretty much decorrelated. We also provide plots of samples attacked with different magnitudes of epsilon and their corresponding predicted quality score by the model. And I think that one conclusion that could be drawn here is that although higher values of epsilon guarantee the success of the attack, this can also be noticed in here. We can still manage to find the trade-off between the visibility of and the effectiveness, the visibility of the perturbation and its effectiveness, as we can still achieve good results for much lower values of epsilon and much less visibility of the perturbation. So to wrap up this presentation, let me highlight the main takeaways. We proposed a framework that enables us to generate adversarial attacks against no reference image quality assessment metrics. We also introduced the targeted setting to the regression context in general. And we did explore the correlation, or rather the presence of an eventual correlation between the attack's performance and its success rate. So that would be all. Thank you for your attention. I don't know if there are any questions regarding the subject.
Thank you. Are there any questions? If there are no questions, I think we are pretty much in line with schedule. So thank you, Hanan. And I believe we can move to the third presentation and the last in this session, which is scheduled to be probably quite a long one. So this is Alban Marie, and the title is let me check. The title is the evaluation of vulnerability of deep learning based image quality assessment methods to adversarial attacks. So, Alban, could you please?
Yeah, I think it was the name of the last presentation.
Oh yeah. So
anyway.
probably it was copy paste in the wrong way. Yeah. Sorry. Yes, that's
no
right.
problem. I will mention the name anyway. So
this is how it is presented in the
okay.
in the schedule. So someone made a mistake. Anyway, okay. I hope we'll learn your correct name of the presentation.
Yes.
So the floor is yours.
Yes. So okay. So can you see my screen?
Yes, we can.
Not yet, but yes, we can now.
Okay, perfect. So so the presentation that I will do today is basically the done that I have done in my PhD. So what I will present today is basically my defense that I did last Friday. So it's very recent. So it was a work that has been done at INSAREN with the supervision of Carole Desnos, Lou Zheng, and Luce Morin. And the name of the presentation is Exploration of Flossy Image Coding Trade-off between Rate, Machine Perception, and Quality. So to start with the presentation, I will first start with an introduction. And for the introduction, I will explain what is video coding for machine, because this field is very related to my thesis. So if we think of what is a machine first, so machine is what, in the context of this thesis, is any kind of vision task that is capable of obtaining a high-level understanding of an image or a video. So there are many different kind of vision tasks. So we can think, for example, the image classification, where we want to attribute a symbol label attribute to one image. We can think of face recognition, where we want to say if two face images are the same person or not. We can think, for example, as object detection, where on top of attributing one label, such as in image classification, we want to also localize with a bounding box the object into the image. And we can also think of segmentation, where instead of attributing one label for each image, we want to attribute one label for each pixel. So for example, in this example, we can attribute one label for the road, a bicycle, the car, and so on. And in the context of my thesis, I will focus on these two vision tasks because they are complementary in a sense that one of them is very high level, as we have to only predict one label, while the other one is much more difficult to do, as much more information have to be predicted. So nowadays, machine vision is pretty used everywhere. So we can think of autonomous driving, smart cities, for example, for traffic regulation. We can think of surveillance application, where we want to understand what's happening into an image without the intervention of a human in the loop. We can think of other applications, for example, in agriculture or even in medical application. So now that we have talked about machine, we need to talk about video coding and why video coding is important in the context of this thesis. So let's start with a very simple example. Let's say that we want to compute a given vision task. And to do so, we will use a camera that will record an image or a video. We will then use directly the vision task after the recorded image or video to obtain the prediction. So this is what we call edge computing. So for example, you use your smartphone to record an image or a video and you want to directly compute the vision task directly after. So the problem with this computing paradigm is that most cameras are very limited in terms of computing resources, and especially for vision tasks, most of them are based on deep learning algorithm, which can be very heavy in terms of computation. So in that case, what we want to do is to outsource the vision task computation to be able to perform them even on even with a camera that doesn't have many computing resources. So this is what we do there. So we just simply outsource the computation to an external server so that we are able to compute the vision task without any problem. There is another problem that is raised with this paradigm, is that it is not possible to transfer raw image or video as they are too voluminous. So we need to use image or video compression for the transmission. So this is what is called video coding for machine, because we are using image or video encoder to transfer a bit stream, and then by decoding the image or video, we are able to compute the vision task. And lastly, there is a last paradigm which is called feature coding for machine. And in this case, instead of computing the vision task on the external server, we split the vision task in two parts. The first part will be compute on the camera side. The second part on the external server. And what is transfer is the intermediary state between the two, which is called a feature map. And in this context, we use a different kind of encoder. And we choose to not focus on this pipeline as because we have to compute the vision task. The first part of the vision task has to be computed on the camera side. It means that we have lower outsourcing advantages. So in the context of my thesis, I focused on the video coding for machine paradigm. And the goal was to focus on this paradigm because most of the data that is being transferred is meant to be seen by a machine only once, and afterward we don't need to store it or keep it to be seen by a human afterwards. We do not need to make sure the quality is high enough for a human. We just need to make sure that the vision task is able to be performed well, and that's it. So this creates a big coding opportunity. So in a nutshell, if you want to summarize the goal of video coding for machine, we have to perform two different antagonist things. The first one is to reduce the bandwidth usage, and also to maintain as much as possible the performance of the vision task. So what are the problems that are created by this pipeline? So the first one is that when we encode a video and transfer it into using image or video encoder, artifacts will be introduced into images, and this artifact will lower the vision task performances. And so we want to ask the question, how can we enhance the vision task resilience to this compression artifact? So the second idea is that nowadays there are many image and video encoders that exist that have been developed throughout the years. So for example, there is a JPEG which is more than 30 years old, and there is other codecs that have been proposed in the recent years. However, most of these encoders are based for human perception. And in our case, we want to not preserve the human perception of image and video, but the machine perception. And in this context, maybe these encoders are not perfectly suited. And also, nowadays, there are other kind of encoders that are emerging, which are based on deep learning techniques, so, such as autoencoder and artificial intelligence. We can think, for example, at few standardization committees that are proposing new standard using such technology. And in the context of our thesis, we choose to focus on traditional encoding techniques, so not encoder based on deep learning. And we choose to focus on this because it creates a backward compatibility with existing cameras that embed hardware encoder and decoder of existing encoders. And also because we can reuse this camera, maybe it will help to lower the mineral resources that is required for this camera, which is beneficial from an ecological point of view. And in this context, what we want to ask is, can an existing traditional encoder that was first optimized for human perception, can this encoder be adapted for machine perception? And lastly, in traditional encoder, the way traditional encoder work is by encoding the image in a block manner. So what if we want to encode an image, we will divide it into various blocks, and each block will be encoded separately. And if we want to encode, for example, a block in an image, we have to think of a way to get an accurate prediction of the block. So maybe we can use the surrounding block to use a horizontal prediction or a vertical prediction that will result in a different residual block that we want to transmit. And maybe one of these two modes will be preferable to encode a given block. And the way an encoder works, it aims to find the best encoding mode for each block, and this is done with a rate distortion optimization, which aim at jointly minimizing the distortion and the rate that is created by transmitting by compressing a block in a given way. And in this context, as we use a distortion measure, we want to ask, is this distortion measure adapted in the case of machine perception? So for this three problematic, we propose to, we have done different publication in this thesis. And today in this presentation, I will present three of them in the following parts. So the first one will be about enhancing the machine resilience to compression artifacts. Okay, so as we saw in the introduction, when we encode an image or a video, artifacts are introduced into image and video. And so because of that, the vision task performance get lowered. So what we want to do is to mitigate this impact by enhancing the vision task resilience to these compression artifacts. So to do so, we will first take a look at the way a vision task is trained. And we will propose two different training strategies to enhance this resilience. So the first one is called progressive training. So let's first take a look at the way a vision task is trained. So we start with a raw image which is uncompressed. If we pass it to a vision task, we can obtain a prediction. And this prediction can be compared with a ground truth using a loss function. So this loss function will help us to get a score that will say if the prediction is either good or bad. And based on this loss function, we are able to do some backpropagation that will help to train the model and with time hopefully get better prediction. And the idea of progressive training is instead of training on raw undistorted image, is to train on image with quality that lower over time. So we'll do a training that starts with image of high quality, and as the training advances, we will lower the quality of images throughout the epochs. And this way, we hope that this will help the model to train in a more smooth manner and obtain better prediction on distorted images. And the way we lower the quality of image as the training advances is determined by this formula, which in short is an exponential decay function. And if we have to take a look at only a single parameter, we can see that we have a parameter S, which helps to control the convergence speed. So in short, higher or lower value of S allow to have qualities that decline very fast or more slowly. And the second proposition that we propose for enhancing the machine resilience to compression artifacts is to add a regularization term to the loss function. So if we go back to this pipeline, we use a loss function to train our vision task. So first, instead of training on undistorted images, we propose to train on distorted images. And second, we propose to add a regularization term, which in short will aim to minimize a distance function. So D there is a distance function, and we will minimize the distance function between the prediction of the model G on undistorted images and the prediction of the model F on distorted images. So in short, the model G and F share the exact same architecture at the difference that the model G is not trained. So the weight do not evolve as the training progress. We use weights that were pre-trained on undistorted images. And the goal is just to make sure that the model F that we want to train is able to do prediction on undistorted images that are as similar as the prediction of the model G on undistorted images. So to evaluate these two propositions, we will compare to different strategies from the literature. So this strategy starts with the step one, and the step one consists of training a model G on undistorted images. And with that, we are able to obtain model weights that we call theta G. And with this model weights, we are able to use other training strategy and to compare to other training strategy. So there is 3 of them. And so the first one is what we call baseline, which simply consists of taking back the model G and taking as input distorted images and see how well the vision task perform. So in this case, as we do not retrain the model G on distorted images, the vision task will perform poorly. So the second step is to do what we call fine-tuning. So we take as input the model weights theta G, and we retrain the vision task F on the distorted images. And that way, we enhance the resilience of the vision task F to distorted artifacts, to distorted images. So in this case, we consider to only one coding configuration for every for every training. So for example, if we want to train on a specific quality of, I don't know, JPEG codec, for example, we will do one training for this specific codec. And if we want to consider multiple coding configuration, we will do one training per coding configuration. And lastly, we have data augmentation, which is very similar to fine-tuning, but at the exception that instead of doing one training per coding configuration, we will consider all the coding configuration at once. So for example, each encoder, each quality, and so on. And in a data augmentation manner, we will use all of this data at training time to train on a single model on all of these artifacts and all of these images. So this strategy has been proposed in the literature in the context of video coding for machine, just there. So if we take a look at the result, so we will consider the vision task, the semantic segmentation vision task. We'll use the Cityscapes dataset and the encoder VVENC, which is based on the VVC standard. So we will consider two different things, which are the training complexity and the BD rate. So BD rate is the John-Teger delta rate. And in this case, if we have, for example, a BD rate of 20%, it means that to have equivalent performance of the vision task in terms of MIOU, it means that we will require 20% more rate compared to the reference. And in this experiment, we compare with reference to the fine-tuning approach. So if we take a look, for example, at the baseline, we can see that we have a BD rate of almost 500%. So this is quite a lot, and this shows that if we want to have equivalent performance to fine-tuning, we require to have much more rate, which means that the machine is not able to have to perform well on distorted content. And on the other hand, if we take a look at the data augmentation technique, we are able to get a much lower BD rate score, but still higher compared to fine-tuning. So this is because the data augmentation consider multiple coding configuration at once, and this create limitation to be able to generalize on all of this coding configuration. However, the training complexity is much lower compared to the fine-tuning approach, as we have to perform only one training. If we compare these techniques with the progressive training that we propose, we can see that, for example, if we take a look at the first line, the fastest progressive training, we can see that the training complexity is lower compared to the data augmentation technique, and we also have a lower BD rate. So overall, the proposed training is better. And if we take a look at the slowest training, we can see that the training complexity is still faster compared to fine-tuning, but we also have a lower score in terms of BD rate value. So we require less rate to have equivalent machine performance. So overall, the progressive training is better compared to existing approach. And lastly, if we compare the two techniques that we propose, so progressive training and the regularization term, we can combine them to see how well they perform. So we consider two vision tasks this time. So at the left, we have the image classification on ImageNet, and on the right, we have semantic segmentation on Cityscape. And again, we compare against the fine-tuning strategy. So the two axes are the same as the previous table. So the training complexity, the lower the better, and BD rate the same. So the best is to be on the bottom left. And as we can see, for both vision tasks, we are able to get better trade-offs compared to the fine-tuning by using both the regularization term and the progressive training for the image classification, and using only the progressive training for the semantic segmentation vision task. So in conclusion, for this first contribution, what we have proposed in this is two different training techniques to enhance the machine resilience to compression artifacts. So we can obtain greater machine performance at equivalent rate. We also have a lower training complexity compared to other training strategy. our techniques do not change the inference time because we only tackle the training part. So once we want to deploy a model into the in a real world application, there is no increase in terms of inference time. But lastly, our progressive training have a drawback as it requires to have multiple DNN weights for each coding configuration that we proposed. So I will now present the second contribution, which is more related to the Kakovia field, as it tackles image quality assessment metric evaluation in the context of machine-to-machine communication. So what is the motivation of this contribution? So if we want to ask the question, let's say that we have an image or a video and we want to assess its quality according to machine perception. So what we want to say is to predict if the image or video is of good quality according to any kind of vision task. So the first approach is to just simply use in a naive way a lot of vision tasks and model and measure how well they perform and therefore determine if the image is of good quality or not. So this is quite impractical and time consuming in a real world application. So instead of that, what we propose is to use image quality assessment metric as it has been done for the human visual system. And in this context, what we want to ask in this contribution is, are existing quality metrics that were first designed for human perception, are they able to also capture machine perception or not? So in short, can we, with this existing metrics, capture the performance and predict the performance of vision task? So in this presentation, in this contribution, what we want to do is to propose an evaluation protocol that will help us to measure this correlation. This that will measure the if this full reference metric are able to capture machine performance or not. So we start with undistorted images, and we can first use a lossy encoder to obtain distorted images. And between the two, we can compute full reference image quality assessment metric that will give us a score to say if the image is either of good quality or bad quality. So second, with these two images, so undistorted and distorted images, we can use vision task. So in this case, we will consider the semantic segmentation algorithm, and we will obtain two predictions. So one on the undistorted images and one on the distorted images. And what we are going to do is to compare the two to have a measure of the performance of the machine. And so one thing that should be noted is that we will compare ourselves with the prediction on the undistorted images. So we do not use a ground truth, and we do not compare ourselves with a ground truth. So instead, because we compare on the prediction on undistorted images, we compare to what is called a pseudo ground truth, which has also been proposed in the literature for video coding for machine. So what we do in this next step is to compare the two prediction map using pixel-wise accuracy to obtain a measure of the performance of the machine. And lastly, if we do this pipeline on a whole dataset and not a single image, we are able to measure if there is a correlation on the image level. So second, on top of measuring the correlation on the image level, we also want to measure the correlation on the block level. So why do we want to do that? So as we saw in the introduction, any traditional encoder rely on a block-based strategy to encode a given block. And this block, because of that, any encoder have to use rate distortion optimization and optimize and minimize the distortion, which is measured on a block level. So by doing that, we hope that the distortion measure is somewhat correlated with machine perception, which means that by lowering the distortion, we will also preserve the performance of the machine. So what we want to do is in this experiment is to measure if this correlation is there or not. So we start with the previous pipeline that help us to measure the correlation on the image level, and we will extract blocks from this pipeline. So we'll have blocks on undistorted images, distorted images, and prediction on both undistorted and distorted images. And after we do the exact same thing, we compute full reference metrics, we compute the pixel-wise accuracy, which is our measure of the machine performance, and we can compute the correlation on the block level. So the one strategy that is used to measure the correlation, something that has to be used to measure the correlation on the block level is what we call block sampling. So in order to sample blocks from the image, we have to use to sample them in a way. So one approach is to do that in an uniform way. So the idea is very simple. It's just you take a block randomly into the image, and every location has the same probability to be chosen. So the problem with this approach is that this creates a dataset imbalance, as we have a very high likeliness to have blocks with perfect accuracy. So I will illustrate this in the following. So if we extract block at a random location, maybe we will, for example, extract a block in the middle of the road. And if we compare the block of the two images, so prediction on undistorted and prediction on distorted images, we can see that the prediction only contain one class for each pixel and for the two blocks. So this means that if you want to compare the performance between these two blocks, we'll obtain a perfect accuracy, as these two blocks have prediction are the same. And in this context, if instead of computing the accuracy for only a given block, we compute it for 1,000 of blocks, we can see that the probability that we have a block with accuracy of 1 or near to 1 is very high, and we have much lower chance to have blocks with lower accuracy. So this creates a problem, because in this case, this means that we will compute the correlation with only values of ones, which is not ideal to compute correlation. So in this context, what we propose is a different block sampling strategy, which we call machine accuracy-based block sampling. So in short, instead of sampling block in a uniform way, we'll sample block at very precise location, which will help us to have as much block between, for example, 0.3 and 0.4 accuracy, and for example 0.7 and 0.8 accuracy. So in this way, the dataset imbalance problem is resolved. So if we take a look at the result, we will first take a look at the correlation on the image level. So we will consider two correlation measures, which is Spearman and Pearson correlation, and we consider various image quality assessment metric. So this work has been published at the QMX conference in 2023, and in the paper we compare with more metrics, but the conclusions are the same. So if we take a look at the correlation, we can see that we have a correlation that are around 0.6 and 0.7. So the correlation is hello, can you hear me?
Yes, we can hear you.
Okay, sorry, I had a microphone issue. So anyway, so the correlation is relatively high. So this means that on average, if we have an image of higher distortion, it means that the performance on the vision task will be lowered. However, the correlation is not that high, which means that these metrics are not perfect at predicting the performance of machine. However, if we take a look at the correlation on the block level, so the correlations that we obtain are not on the same level. So we can compute the correlation at different block size. So for example, 32 by 32 or 128 by 128. And as we can see, we have correlations that are much lower. So at the lowest, we have a correlation of 0, so no correlation at all. And on the best, we have correlation at around 0.3. So there is two different things that we can see. The first thing is that the metrics that perform the best are the ones that are based on deep learning, and older metrics such as SSIM or PSNR doesn't work as well. And second, as the block size gets lower, it is harder and harder to obtain good correlation. So for example, if we take a look at the correlation on bigger blocks, it is higher compared to correlation on smaller blocks. So this is a problem because traditional encoding technique, which rely on block-based encoding, will have to encounter small blocks, and so the distortion measure that will be minimized into this encoder is not correlated with the performance of machine, which means that we minimize something that in the end doesn't really matter because it doesn't preserve the performance of the machine. So as a conclusion, so in this contribution, we have proposed a study to evaluate the correlation between existing full reference image quality assessment metric and the performance of the machine. We have proposed a novel evaluation protocol in this context. And as we saw, there is an existing relatively high correlation on the image level, but we have a very low correlation on the block level. And this low correlation on the block level implies some sub-optimality in traditional encoding techniques because they are based on block-based strategy. Okay, and in this last contribution, I will take a look at the rate distortion optimization more deeply, and we will see if we can improve the way a video encoder works in the context when the image and video is meant to be seen by a vision task. So, as we saw in the introduction, the rate distortion optimization aim to find the best encoding mode for a given block, and in order to compare every existing encoding mode, so for example, in this example, we have horizontal prediction and vertical prediction, we want to answer the question, which encoding mode is the best in the context of to compress this block. And in this context, we want to minimize we want to perform the rate distortion optimization, and to do so, we minimize the distortion and the rate at the same time. But as we saw, when we want to minimize the distortion, the measure that is used for the distortion is not correlated with machine performance. So this means that we will minimize something that will, at the end, maybe not matter to preserve the machine performance. So in this context, what we propose is, instead of using the SSE, which is sum of square error, so it is a simple L2 norm, we want to use instead a metric that we'll propose specifically for machine perception, which will be based on deep learning and which hopefully will better capture the performance of the machine. And so by minimizing this metric, maybe this will allow us to have greater performance, a greater trade-off between rate and machine performance. So in the next slide, I will present the way our metrics work. So similar to SSE, our metric is a full reference metric. So we'll compare an undistorted block with a distorted block. We will first use a feature extractor to extract some feature map on both blocks. We can then use average pooling to have a smaller feature map. The two feature maps can be concatenated together. We can use a multi-layer perceptron to obtain a score and finally a sigmoid to obtain a score between 0 and 1. So in a given encoder, the block that can be encountered can be of very various size. So if we take a look, for example, at the VTM encoder, the block can have size that vary between 4x4 and 64x64. And as we saw before, it is very difficult to obtain a good accurate prediction on a block as small as 4x4 because the size of the block is so small that it is impossible to have any context of the kind of data that it represents. So as it is very difficult to obtain a good prediction of the machine performance on this 4x4 block, what we will do instead is to use additional context that we have available at the encoder side to hopefully get better prediction. So to do so, what we can do is to use additional information. So for example, if we take a look at the distorted block, we do not know how the surrounding block will be encoded, but we do know how the original image looks like. So we can, for example, instead of using a very small block, for example, 4x4, we can use additional context. So instead of using the coding unit, we will use the coding tree unit in the VTM. And also, we can use the chrominance information as it is available also in the original image. And because we use a bigger block, we obtain a bigger feature map. And to obtain information that is only at the original block into the coding tree unit, we use a mask to to perform the average pooling only on the corresponding area in the feature map. So in order to train this metric, we'll have to use some to first obtain some block and training label to train this metric. So what we'll do in this context, we will go back to the pipeline that we proposed in the previous contribution, and we will again extract blocks from this pipeline. And so we obtain 4 groups of blocks. And the first 2 are the blocks on undistorted images and distorted images. And these 2 can be used as the training lab and the input of our metric of the proposed model. And the last 2, the prediction on undistorted and prediction on distorted images, can be used to have measure of the can be used to have a measure of the machine performance with again the pixel-wise accuracy, and we will use this pixel-wise accuracy as the training label. So we will try to predict this this accuracy. And lastly, as our model have to perform well for various block size, we consider various block size at training time, and to avoid overfitting problems, we choose to train on the testing set to extract blocks and not the training set, as the training set was used beforehand to get this prediction, to train the semantic segmentation models. So first, we'll take a look at the correlations that we obtain between our proposed metric with machine performance. So we compare to other kind of metrics. So for example, we have SSE, SAD, which are L2 and L1 norm. We have SSIM. We compare to DISTS because it was the metric that performs the best in the previous contribution. And we also compare to feature SSE and feature SAD as it was proposed in the literature in the context of video coding for machine. And these 2 metrics, in short, they are the same as SSE and SAD, but instead of computing the L1 and L2 norm on the pixel domain, we'll first extract a feature map using a VQEG classifier, and afterwards we will compute the distortion on the feature map and not on the pixel on the blocks. And if we take a look at the correlation, we can see that our metric, because it is based on a learning strategy, is able to get better correlation with machine perception. And something else that we can see is that the speed that the correlation on the smaller block is smaller compared to the correlation on bigger blocks, but compared to other metrics, our metric is able to lose less correlation as the block size lower, and this is because we use additional context as input of our metric. So lastly, what we want to do is to integrate this metric into a given encoder and hopefully achieve better coding trade-off between rate and machine performance. So something that we have to take care of is what is called the additivity property. So let's say that we want to compare two encoding mode. So one of them is to the no split mode, and one of them is ternary split mode, where the 3 sub-blocks will be encoded separately. So in this context, the rate distortion optimization is computed for all of these sub-blocks and is summed together for the ternary split to be compared with the no split mode. And because our distortions that we propose give a score between 0 and 1, and there is more sub-block in the split encoding mode, our distortion, as it is computed 3 times there, we can have a score between 0 and 3 for the distortion, while in the context of the no split, we can have a score only between 0 and 1. So in short, because we want to minimize this will to minimize the rate distortion optimization, this will falsely favor the no split category. So to avoid this problem, we choose to ponderate the distortion measure by the number of pixels that we have within each block, which will avoid this, which make sure that we preserve the additivity property. And lastly, in the rate distortion optimization, there is a lambda, which is called the Lagrange multiplier, which was tuned for the original distortion measure. And in our case, because we change the distortion measure, we also have to adapt the Lagrange multiplier for our new distortion measure. So to do so, I will not enter into much detail, but we do a least square optimization to obtain suitable Lagrange multiplier with our new distance function. And lastly, if we take a look at the result, so for now, so the result we compare against an encore, which is a VTM encoder, and we integrate our metric within the VTM and see if we can obtain better performance. So both axes, the axis on the bottom represents the rate, and the other axis represents the machine performance. So the best is to be at the bottom, at the top left. And as we can see, we do not manage for now to achieve greater trade-off between rate and machine performance. So in conclusion, for this contribution, what we propose is to integrate learning-based quality metric in the rate distortion loop of an encoder. So we take advantage of additional information that is available at the encoding, to obtain better prediction. So while we are able to obtain greater correlation with machine performance according to our experiment, but despite that, we are not able to achieve greater trade-off between rate and machine performance. So there are multiple reasons that could explain this, and I will discuss them soon in the future work section. So as a general conclusion, in my thesis, I proposed multiple public contribution and publication that focus on various parts of the video coding for machine pipeline. So this contribution, some of them are complementary with a standard that might emerge in the case of machine vision. So if we summarized the contribution, So the first one aimed to enhance the resilience of compression artifacts, and we propose two different training strategies to enhance the vision task resilience to various kind of compression artifacts. In the second contribution, we show that our experiment reveals that traditional encoding technique might suffer from a suboptimality because they are the encoding is based on a block-based strategy, and the distortion measure is not able to correlate with the performance of machine on a block level. And lastly, on the last contribution, we try to propose a distortion measure that will be better suited for machine performance, but unfortunately, we were not able to achieve greater trade-off. So I think I will not go too much into detail into the future work, but one future work will be to investigate on the reason why this last contribution doesn't work very well. And there is other future work, but again, to be fast, I will not enter into too much detail. So thank you for your listening, and if you have any question, you are welcome to ask them. So thank you.
Thank you. First of all, congratulations on your doctorate. And I see you're welcome. So I see Margaret, who probably wants to ask a question. So Margaret.
I do. So thank you very much for sharing this with us. One question, that last point you made, that the metrics that you looked at don't work well with the at the block level.
Yes.
Will you be able to share any of that data for other people to look at?
You mean the data set, or like to reproduce the results?
Not to reproduce the results, but to try other metrics on your blocks.
Okay, so on the paper we compare to more metrics. So we consider many metrics from the literature, maybe 10 or 12 of them. But so if someone wants to compare to another metric, what we hope to do is to make this code available open source, so anyone can basically compare another metric with on the same experiment that we did.
Okay, thank you.
Thank you, Margaret. I see Ioannis with a question. Please go ahead.
Hi, Alun. Very good work. And I missed maybe some parts, so I'll go back and revisit. But in summary, how do you address the problem of the, as I say, region of support, right? I'm picking SSIM as an example. SSIM uses an 11 by 11 filter to calculate its metrics. So if I want to apply it on any block, I need actually a region that is bigger than that. How do you address that region of support for all these? You know, again, GPS are simple, but the ones that require more than that.
Yeah.
My first question.
So yes, exactly. So this is a very good point. So you mentioned SSIM, which have some issue on very small blocks, and there is also other metrics. So for example, the matrix LPIPS is not suitable on very small blocks. So in this case, maybe this metric could be either changed a little bit. So for example, in the case of SSIM, what we did is to consider a smaller kernel size to be able to compute it on smaller blocks, and some metrics we were not able to compute them on a smaller block size. So for example, in the case of the image level experiment, we consider MS-SSIM, but on the block level, because of the multi-scale strategy, it is not suitable. So in some case, you can adapt the metric. In some other, it might say that the metric is not suited for this specific use case.
Thank you. And just a comment on the very high level strategy, I think you answered very well. I personally think that the direction you have taken on using, let me use the word traditional codecs, is the most viable one. And very recently, actually at ICIP, I heard some contributions for people who for example, suggested a neural network-based compression scheme to be used for this purpose, right? Where, of course, one needs to ask, if you don't have the compute to run the vision task, how do you have the compute to run a very, very complicated neural network-based codec. So I would say the balance of complexity is a very difficult one. So I would say I'm a believer that the moment we reach enough complexity on the device to run very highly sophisticated codecs, including the new generation of neural network codecs, at that point, you probably can solve the vision task on the edge, right? So this is my philosophical standpoint. And because of this one, I think that the approach you are overall taking is the most practical and good one. So congrats again.
Thank you. Yes, I think it's a very clear point that has to be made, and you got it very well, because most people in the literature, in the context of video coding for machine, will work on end-to-end encoder because they are able to achieve very high gain in terms of trade-off between rate and machine performance. But it is at the cost of having a very complex encoder, and at the end, it doesn't make sense because the point of using an encoder is to outsource the computation. But if your encoder is more complex and also based on deep learning, similar to the vision task, there is no point of doing the compression to transfer the computation, because you do more computation to outsource the computation. So that's one of the reasons we choose to focus on traditional encoding.
Okay, I think there is a question coming from Andreas.
Yeah, thanks for your interesting talk. I didn't quite understand. Are you integrating this full reference metric inside the codec, or because my question behind that is, how do you get access to the distortion that are produced by any video codec for the evaluation of your metric? Yeah.
Okay, so we do integrate inside the codec. So we are basically the fact that we change the distortion measure, it means that we will change the way the image will be compressed. So for example, I can show you an example. No, it's not this one. Okay, this one. So maybe the image quality is not good because we are on remote, but on the left, you can see an image that is compressed with the metric that by adding the metric that we propose inside the encoder. And at the right, you have the conventional encoder. And maybe, I don't know if it's clear enough on the visual, but
we
as you can
see clear differences.
Yes, the images are very different because there is some problem into the last contribution, but we can see that it's changed the choice that are made by the encoder to encode the image. So if it works, which is not the case, hopefully it will help to get better encoding mode that are more suited for machine.
Okay, because in that case, you have to run, I don't know, like for each block, maybe 1,000 times for each of the partitioning mode, you need to run your metric. So is there like some overhead complexity or this kind of thing? Yeah.
So yes, of course. So if we take a look at the original contribution, what we did is to replace the SSE function, which is simple pixel-based L2 norm, by a deep learning model. So of course, as you mentioned, this metric is called thousands of times, sometimes even million of times in the VTM only to encode one image. So there is a big overhead in terms of complexity. So the point of using such deep learning metric, which is heavy, very heavy, was the goal was to not to propose something that will be suitable into a real world application. The goal was to do a proof of concept, because this approach of changing the distortion measure has not been explored in the literature whatsoever. So what we wanted to do is first, by taking an unrealistic metric that will be able to hopefully better capture the machine performance, we wanted to see if in this context, at least, we are able to achieve better coding performances for machine. And so this was not clear if it was possible or not. And at the end, it appears that it is not so easy to do, because we were not able to achieve greater trade-offs. So this work was just as a proof of concept, and if we were able to obtain better trade-off, the goal was to not keep this EV metric, but to propose one that is much shallower and, for example, based with uncrafted feature and so on, something else that will be much more lightweight.
Okay, thanks. Yeah, because Patrick sent me your thesis and some paper that was related to that. And in the paper, I was thinking you were saying like you compute all of that before the encoding, and that you could leverage that inside the encoding and just changing some lambda or something like that by weighting the lambda. But maybe I will send some email or this kind of thing. Okay,
Yes,
thanks.
feel free.
Thanks
I
a
will.
lot.
Yes, thank you.
Okay. I see there is a question coming from Celine Reza. It's in the chat. So Celine, can you express your question using the microphone, or you need me to read it loud? Selim? Okay, maybe he has some
Thank
problems with the
you.
microphone. So, oh yeah, yeah. So can you maybe ask your question?
Okay, thank you.
Yes.
I want to say that one thing, when background image, if we collect from satellite view or state view without camera and match with captures image that is already taken from camera, I think image quality will be better than camera when it is running object. So my question is, it is possible to integrate satellite view image or state view image, background image with camera image, and it is only for clear image. So my point is, I want to say it is possible that we want to integrate camera image with other image. It is possible. It's my curiosity. Thank you.
I'm not sure I understood your point. So you want to integrate satellite images with conventional camera? So I'm not sure I got the question. I'm sorry.
Nowadays, we know that camera image is depends on what is the pixel quality of camera we are taking. But it is I am giving more emphasis in only object that is moving, but background is image quality is, I think, well. And my one question is, I want to giving more emphasis object when we are detecting.
Okay.
And background image is not changing. We can get good quality image from image view or satellite view. Already it is stored previously. Thank you.
Okay, I see. So maybe I got a bit better understanding of your question. So maybe in the case you have a camera that is stationary, where basically almost everything in the camera is fixed, so nothing is moving except a small object. So in this context, if we want to do some image quality assessment metric, maybe it will be more suited to do this evaluation only on the part that is relevant. So maybe on the part that is moving and not on the background, which doesn't really matter maybe for the vision task. So that's one point. And another point is that this encoder, one strategy for the video and image coding in the context of machine will be to use some saliency map to guide which area of the image should have more rate available to better transmit a given part of the image. So in this case, if you have a stationary part that doesn't move, maybe you do not want to allocate that much rate to it. And in this context, maybe image quality assessment metric could also rely on saliency to guide which area is more important to predict the quality. So if maybe I didn't took perfectly your question, so feel free to ask me by email or if so.
Okay, thank you. Are there any further questions? If not, I still have one question. I hope it's going to be a very short one because we already had a couple of questions. So just I was interested in the there is some noise. I don't know who is making this noise. It's someone's child, I think. Okay, so my question is concerning the database you use in the second contribution. Was it the Kitty database or some custom database of the videos that you used?
Okay,
just for the curiosity.
Yes. So in the second dataset, in the second contribution, sorry, I consider so the cityscapes dataset, which is which contain videos that are recorded from a car that is driving into German cities, and it's only urban landscapes. Yes, it's single images, not videos. So cityscapes dataset.
Okay, just maybe a small comment. I'm sorry.
Yes.
If you want to look into some more databases, there is a database called New Scenes. I don't know if you know it. It also contains scenes coming from Asian and American cities, which have a slightly different modality. So, I mean, European cities have a slightly different modality than Asian cities and than American cities, because of some characteristics. So if you were like looking into some more diversity in the source databases, you can consider the New Scenes database. I can type in the name in the chat soon. Okay. Okay, that was like everything. I will probably try to not to extend it anymore because we already had like 1 hour and 40 minutes of the Cracovia session, which is probably more than we scheduled initially. So if there are no further questions, then thank you. And thank you, Avan. So great presentation, and I think it's everything that we have scheduled for Cracovia this time. So this concludes the Cracovia session, and I give the floor back to Charles and Margaret.
Hello. Yeah, I think it's just to hand it over to Pablo for the 5G KPI.
Right, thanks, Shell. Let me share my screen. So we only have one presentation in the 5G KPI session, which is basically intended for